morning, students. In my third video, today we will discuss about the potential energy of a system of charges. So, potential energy, this is electric potential energy of a system of charges. Okay, already we have discussed equipotential surface and electric potential. So today we'll discuss about the potential energy. Now, potential energy, how we calculate electric potential energy. You know that, say there is a charge Q1 here, any position, say it is P1 position, and there is another charge Q2 and it's at infinity. Remember, and then you take it from infinity to this point. Say this is the point, you can consider it as P2 point, and you take charge Q2 from here. Now the distance between the two charges is, say, R12. 12 is the reference point. So electric potential now at what? Q2 due to Q1. So if I ask you what is the electric potential, V1 is the electric potential. V1 is the electric potential of Q1 at point P2, KQ by R. So 1 upon 4 pi epsilon naught, it will be Q1 by the distance is R12. So this is the potential. Now if I ask you what is the work done, now say W is the work done. W2 we can consider as the work done. Work done in moving Q2 from infinity to what? Point P2. Okay. And what we have heard about is that work is what? Potential into charge. So potential into charge. And what is the potential at this point? Is simply V1. What is the charge? Q2. So V1 will be 1 upon 4 pi epsilon naught Q1 R12 into what? Q2. So this is the work done. You remember the general formula was what? K Q1 Q2 by what? R. So if I ask you what is the work done? So work done is stored as potential energy. Which energy? Potential energy. And complete is electric potential energy. So this is the work done. If you see, it is stored as electric potential energy. So very simple. There was a charge Q1, you took a charge from infinity. Then you know that V1 is the electric potential at this. V1 will be this. What is the work done from taking W2? Work is what? Potential into charge. Potential is V1 into Q2, and this is the work done. And now, you know that if you have a two charges, you will find out the work done. If again there are three charges, say Q1, Q2, Q3, I'm talking about the three charges. So potential energy, we can get it. You remember, it is just like gravitational potential energy. So potential energy of system of three charges. There are three charges. Okay. So you know that how you calculate it. Say this is R12, this is R13, this is, say, R23. And these are the charges being taken from one point to the other point. If I ask you what is the net work done, so you know that U1 plus U2 plus U3, remember gravitational potential energy, and then U1 is in between these two charges, U2 is this, U3 is this. So can I write K Q1 Q3 by R12 plus K Q2 Q3 by R23 plus K Q1 Q2 by what? R13. So this will be the net potential energy. Remember, work done is final potential energy minus initial also. So this is, and one thing I want to ask you, if any charge is here, what will be the potential at infinity? So we know that it is kq by r. When r is what? Infinity, potential is what? Zero. So potential of a charge at infinity is what? Zero. So this is the potential energy of system of three charges. And then you know that I can give you an example here. Before going that, there are four charges. And I think you have done this example in class 11th also. You remember it. There are four charges, say uh, plus Q, plus Q, plus Q, and plus Q. And this is a square of side A. Okay. And then you know that across the diagonal also. And if the question is that find the work done, find the work done in say assembling charges from infinity. Now you have assembled in a square of side A. Now that means that work done will be what? Work done will be final potential energy minus initial. So work done in assembling charges from an infinity. Infinity is U initial. U initial will be what? Zero. Okay. So you have to calculate U final. So U final will be what? U1 plus U2 plus U3 plus U4 across the sides U1, U2, U3, U4. And you remember across the diagonal it will be U5 and U6. So that is U5 plus U6. You remember it was a question in class 11th also in gravitational. And all four are same and all these two are same. So final potential energy will be 4 times U1 and 2 times U5. All four are same. How? See here. 4 U1 is k q into q by a plus 2 u5. U5 is k q into q. And what is the distance between these two charges? Is what? A root 2. So it will be a root 2. So if you calculate it, it becomes 4kq square by a plus 2kq square by a root 2. So what is the work done? If you see, final potential energy is this 4kq square by a plus 2kq square by a root 2 minus 0. So even we can write it like this, kq square by a will be common, and bracket it will be 4 plus this can go by root 2 times. So 4 plus root 2. So this is the answer of what the work done in taking charge from infinity to a square. So this is very simple. We have gone through gravitational potential energy, how you calculate it. All were at infinity. So initial is what? 0. Final will be at this. 4 will be through the sides and 2 will be across the what? Diagonal, and all will be same. The magnitude is 4 times of this and 2 times of this. So this is how we are going to define the electrostatic potential energy. Now we'll talk about the other thing is that behavior of conductor in electrostatic fields. So we are talking about the conductors in electrostatic field, how they behave, how the conductors they behave in electrostatic fields, and even we can say that electrostatics of conductors. So we are talking about electrostatics of conductors. So there are some properties. Some we have already discussed, so we'll discuss one by one. They may be asked as a conceptual one. First is that net electric field is zero inside the conductor. So very simple how it is. We already know that the inside the conductor, we can't apply the Gauss theorem also. So I am going to give you an example. Say there is a plate and this is a positive plate. Okay. And this is a negative plate. If you put a conductor here, do you know what happens? If you put a conductor, this positive will attract negative on this side and this negative will attract positive on this side of the conductor. So the electric field is going from positive to negative of the plate. So this electric field is which one? External one. Okay, and there will be an internal electric field. This is external, this is internal. So net electric field inside the conductor will be what? Zero. Why? Because E external is also E and E internal is also E, because the same value will take, and because both inside the conductor will be what? E external minus what? E internal. So always remember, inside the conductor the electric field is what? Zero. So charges are on the surface. Okay, so there is no electric field inside and this positive will induce negative and this negative will induce positive. So net electric field inside the conductor is what? Zero. So this is one of the property. Second is that just outside the surface of a charged conductor electric field is, so electric field is normal to the surface of a charged conductor. This also we have discussed. Electric field lines are normal to the surface, to the equipotential surface. And this is also very simple. Why? Because if electric field is tangential, say it is tangential on surface, then what happens? It will cause flow of charges or surface currents. Surface current will come on. Okay, but in electrostatics, when we talk about the statics, no such current exists. No such current, remember, exists. Hence, we say electric field is what? Perpendicular or normal to the surface of charged conductor. So remember, this is very important. Charged conductor. So if you take tangential, then there is something which we say cause of flow of charges, and there will be surface current, and no such current exists, and we say that this is. So this is the second property. First already we have discussed, this is the second property. And then what is the third and fourth property that we are also going to discuss is that the next third property is that the net charge on the conductor is on surface and inside, that, and no charge resides inside it. That means there is no charge in the interior. The net charge is on the surface of conductor. So what does it mean? I will explain you. Say there is a conductor. This is a conducting surface. And we all know that the charge is this on the surface. And this is the electric field, this is the electric field, this is the electric field, this is the electric field. And do you know, this is like a Gaussian surface. And this is the main surface of the conductor. And what is the electric field is what? 0. We all know that phi is what? Q by epsilon naught. We have already discussed. Inside conductor, what is the flux? You remember, it will be 0. Charge will lie on the outer surface. If flux is 0, so Q will be 0 inside it. So no excess charge inside it. So remember, entire charge is on the surface of conductor. So this is also a property. So net charge, already we have discussed this in Gauss theorem also. So this is another. Now the next property is that there is another property, that potential, that this is the property, what? Potential is constant. Potential is constant within and on the surface of conductor. So this also we have discussed how. I will show you equipotential surface on the surface of conductor. Do you know potential gradient last class? So this is property number, what was the potential gradient? Minus dV by dr. So if I ask you, remember that there is a charged spherical cell, already we have discussed it. Do you know that inside it electric field is 0? Here the electric field is 0. So dV by dr will be 0. What will we be? Tell me. Constant. So we will be same. We will be same on the surface and inside the surface. So this is how we say equipotential. So this is how V is what? Constant. So this is, we talk about the equipotential surface. Already we discussed this. And then there is another property, and that is property number 5, and that is electric field at the surface of a charged conductor. Charged conductor is proportional, you remember, to the charge density, that is surface charge density. So this is the next property, surface charge density is sigma, and what we do, that we take an irregular surface here, and then on irregular surface, what we take, we consider that a Gaussian short cylinder. So short cylinder is considered here. It is like this because there will be a charge on its surface. This will be like this. And this is having what? Delta S is the surface area. Where is the electric field? This. Where is the delta S area vector? Outside. And we know that E delta S, E ds will be what? Phi. And what will be E delta S? Phi is, you remember, Q by epsilon naught. And how many of you remember sigma is Q by what? Delta S. Charge per unit surface area. So Q will be sigma delta S. So E delta S will be sigma delta S by epsilon naught. So what you get is that sigma by epsilon naught. So this is, and it is what? normally outward. So it is normally what? Outward. So this is another concept, that this will be the electric field. And remember, electric field is zero inside the conductor. So this is the property of the fifth property. Electric field at the surface of charged conductor is proportional to the surface charge density. And last one is the what? It is that electrostatic shielding. Now, before going to electrostatic shielding is another property. We can talk about that also, electrostatic shielding. Now, electrostatic shielding is what? A concept that if there is a charged conductor, now we know that the charge rely on the surface. Now what this property says is that if there is a cavity inside it, like this, and what happens if there is a cavity, what will be the electric field inside it? Zero. And V will be what? Constant. Potential is constant. And electric field is what? Outward, like this. This is an electrostatic shielding. And V is what? Constant, but electric field is what? Outside it. It's like a Gaussian surface. So electric field vanishes in the cavity. So why we say electrostatic shielding? It vanishes in the cavity of a conductor. So electric field is zero. And you know the phenomena of electrostatic shielding, electrostatic shielding is based on that electric field vanishes inside the what? Cavity. So cavity of a hollow conductor. Remember, there's an example that when the lightning takes place, it is better to move inside a car rather standing near a tree. Why? Because inside the car you will feel safe, because electric field will be what? Zero. Say you are inside the car and you know that it forms a cavity here, and electric field will be what? Zero. If the lightning is taking place, if there is a lightning on it, do you know what will happen? The lightning will pass to the earth. So this is how we say that electrostatic shielding. So this is about the electrostatics of conductors, behavior of conductor, and thank you and watch my videos.